Hi, this is Lecture 12, Take 2 of Probability. So what we're going to do today is we're going to talk a little bit about probability density functions. We're going to talk about expected values. We're going to talk about Taylor series and ways to view Taylor series and moments in a very similar mindset. We will see that real analysis is one of the hardest subjects in mathematics. Who's taken real analysis? You passed the hump. For those of you who haven't taken real analysis yet, I strongly urge you to do so. It will give you the language you need to deal with a lot of these convergence questions. It is an absolutely essential subject. How many of you remember your trig? How many of you can prove your trig identities? Alright, I will try to derive every trig identity in 3 minutes or less later today. And so hopefully somebody will have a good stopwatch. If not, we can always go back and look at the tape. Alright, has anybody seen the Cauchy distribution in the stats class? Anyone seen the Cauchy distribution? Okay. The Cauchy distribution is one of my favorite distributions because it has some strange properties. So let's start off with f of x is 1 over 1 plus x squared. So I want to see if this is a probability distribution, and if not, if I can fix it. So there's 2 properties I need to check. What's the first one? Yes?
That it's non-negative?
Non-negative. So f of x greater than or equal to 0, yes. The second one, what's that?
Integrates to 1.
Integrates to 1. That's a little bit harder. Anybody remember what this integrates to? Yes? Close. Well, I'm asking from minus infinity to infinity, so I need a number. So arctangent does play a role.
Arctangent is from infinity to infinity.
So it integrates to pi. So when you look at this, the question should be, why is pi coming into play here? So this is a chance to just review some material you should have seen in probably Calc 1. And just to see how useful stuff like this can be. Before that, it's worth checking, should this integral exist? So when you're integrating functions, you often worry about, does it blow up anywhere? So, does the integral exist? 1. Are there any blow-ups? And the other one is behavior at infinity. So for this problem, we don't really have to worry about blow-ups. Is the denominator ever 0 for real numbers? There's no value of x I can put in such that this blows up. If I gave you the integral of 1 over x squared, then that would be different. Okay? So I don't have to worry about any blow-ups. I do have to worry about the behavior at infinity. So the question is, how do I estimate the behavior at infinity? Well, for this problem, if I integrate from some big number b to infinity of 1 over 1 plus x squared dx, this is less than or equal to the integral from b to infinity of 1 over x squared dx. I make the denominator a little bit bigger, so this will be an upper bound for the integral. And the reason I do this is now I know an antiderivative of 1 over x squared. So what function has derivative 1 over x squared? Calc is prereq, everybody should be shouting, yes.
Negative 1 over x.
Negative 1 over x. So what I'm going to do is I'm going to do 1 over x, and I'm going to switch the order of the bounds because of the minus sign. The minus sign allows me to switch the order, and then this just gives me 1 over b, and that's fine. So this proves that the function is integrable. Unfortunately, it doesn't tell us what it is. However, it's some number, it's some finite number, so there is a normalization constant. It would be nice to know what that normalization constant is. And this is, again, one of the reasons why we care about all these results from calculus from days of yore. So what I'm going to do is I'm going to quickly review the exponential function, I'm going to quickly review the chain rule. These are the calculus techniques we're going to need for a lot of these problems. And I'm going to assume that most people have either not seen or have forgotten these results, so this is a good review. Okay. So let's start off with f of g of x equals x. So if we have a pair of functions like this, we say f and g are inverse functions. The derivative of both sides is fairly easy. One side is the chain rule. So by the chain rule, we would get f prime at g of x times g prime of x. And what's the derivative of x? 1. So what we can do is we can say that g prime of x equals 1 over f prime of g of x if f of g of x equals x. This is an extremely useful relation. How many of you use this relation in calculus to pass from the derivative of the exponential function to the derivative of the logarithm? I'm seeing like one hand kind of go up. A few more. Okay? This is one of the greatest uses of the chain rule. So we can use this to try to get the derivative of, or the antiderivative of 1 over 1 plus x squared. So the method of divine inspiration is one of my favorite methods to look at. Okay? Let's look at the function tangent of x. If you had to apply a function to tangent of x, what function would you like to apply? What function would you want to apply to arctangent of x? Tangent. So what is the tangent of the angle whose tangent is x? X. Right? Proof by English. Okay? We can now use this result here. And we get arctangent prime at x is 1 divided by tangent prime at arctangent of x. Who remembers what the derivative of tangent is? Yes?
1 over cosine squared x.
Good. It's 1 over cosine squared. And 1 over cosine squared is the same as secant squared. So this is the same as secant squared arctangent of x, or 1 over cosine squared arctangent of x. And again, I have complained numerous times about how horrible it is that secant and cosecant are not matched up to sine and cosine respectively. Secant goes with cosine. Right, so here's a formula for the derivative of arctangent. The derivative of arctangent is secant squared of arctangent of x. The question is, can we simplify secant squared of arctangent of x? Probably, given the fact that I'm lecturing on this right now. And if you had to guess, what might you guess secant squared of arctangent of x is?
X squared plus 1.
Okay, x squared plus 1 is a good guess. Any other guesses?
Oh, no, 1 over that.
Or 1 over something involving 1 plus x squared in a very nice way, based on the fact that I've started the day with this function 1 over 1 plus x squared, and then segued into this immediately. So let's try to figure out what secant squared of arctangent would be. So I want an angle whose tangent is x. I need to choose the hypotenuse, the adjacent, and the opposite. Well, if I want the tangent of theta to be x, the simplest way to do that is to put an x here and a 1 here. What would be the hypotenuse? You know, I think people mumbled 1 plus x squared square root. We'll prove that in a few minutes. Right? Now if I want to calculate what is the cosine of this angle, it's 1 over the square root of 1 plus x squared. So I want to make sure I'm doing things correctly. Okay, so now cosine squared is, I think do I have an extra 1 over? The derivative of tangent, the derivative of tangent is secant squared, right?
Yes, it is.
So this needs to be a 1 over secant squared, and this needs to be a cosine squared. Because tangent was in the denominator. Okay. And so now cosine is 1 over square root, so when I square it, I get 1 over 1 plus x squared. So we actually have a nice antiderivative. You know, if I want to know what function has derivative 1 over 1 plus x squared, it's arctangent. We've just shown the derivative of arctangent is this. So if I want to integrate from 4 to 5 of 1 over 1 plus x squared, this would just be arctangent of 5 minus arctangent of 4. So now we can go all the way back to our original function and try to figure out what do we need to do to have it have integral 1. So the integral from minus infinity to infinity of 1 over 1 plus x squared dx would just be, I can have an arctangent at infinity minus an arctangent of negative infinity. Rather than doing that, I want to simplify things. This is the same by symmetry as twice the integral from 0 to infinity of 1 over 1 plus x squared dx. Which is then going to just be twice arctangent of x at 0 and infinity. So what angle has a tangent of 0? 0. What angle has a tangent of infinity? Pi over 2. Is it 90? What do I write here? Do I write 90 or do I write pi over 2? Pi over 2. Whenever we're doing things with differential calculus, it's always in radians. The derivative of sine is cosine only if you're working in radians. Otherwise, there's a conversion factor. So this will give us 2 times pi half, which is just pi. So now that we have this, we actually have the correct normalization factor. Okay, this is why we needed to just have this little detour and remind ourselves of some results from calculus. So this gives us the Cauchy distribution. It's 1 over pi, 1 over 1 plus x squared. And this distribution has a lot of wonderful properties. We'll talk in a little bit about the mean and the variance and expected values. This is not going to have any moments. If you want, we can get into an argument as to whether or not it has a mean. And just to give you a sense of, have you prepared enough for today's class? You should know what I mean by mean and expected values. As long as those words are familiar and you have a rough idea of what that definition is, you've done a good job of reading for this class. If this is, speaking Greek right now, then this means you need to spend a little bit more time reading and have a sense of what's going to be talked about. You can have arguments, and depending on how loudly you argue, you can convince me it has 0 mean. But beyond that, there will be issues. Okay. So this is the Cauchy distribution. We will return to it in a little bit. What I want to do now is I want to do a quick review of trigonometry. It'll allow us to introduce the exponential function, which we're going to need for a variety of things. The exponential function will allow us to talk about Taylor series, and Taylor series will lead very naturally to moments. So this is a good way to review material you've hopefully seen, prepare you for real analysis if you haven't seen that, and put some stuff in the bank for what we're about to do later. I can think of at least 2 different definitions of e to the x. Can somebody give me a definition of e to the x? What's the definition of e to the x? Yes?
A non-zero function that's its own derivative.
Ooh, okay. So then the question is there a unique function that's its own derivative? And so this then gets into differential equations. So this is one great way to define it. So that is one way. So it is the solution to f prime equals f subject to an initial condition. Does anybody remember series expansion for e to the x?
1 plus x plus x squared.
1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial. And you can see when you differentiate term by term by term, you'll actually get it back. If we want to write this in summation notation, it's the sum and goes from 0 to infinity of x to the n over n factorial. This is yet again another reason why 0 factorial should be 1. It allows us to cleanly write this. How many of you have done economics? You might remember the compound interest formula definition. E to the x is the limit as n goes to infinity of 1 plus x over n to the n. This is another definition of e to the x. We're not going to really use this definition that much. But it's worth just remembering that this is another way to define e to the x. We would love to say the derivative of e to the x is e to the x. In order to do this, we would have to justify interchanging an infinite sum and a derivative. A finite sum and a derivative I can interchange at will. An infinite sum and a derivative, you have to be more careful. I can't remember if in one of the appendices in the book I go through the justification. For e to the x, it's not that bad because things converge very rapidly, but it does require work. And so I'm not going to prove rigorously that e to the x is its own derivative. Okay. What is e to the x times e to the y? Yes?
E to the x plus y.
Y. Why is e to the x, e to the y equal to e to the x plus y? Yes?
When you do the log product of the sum.
Haven't even introduced the log function yet. We don't have the log function yet. Yes?
Well, because e to the x is just e multiplied by itself, x times, and
Okay, so what does it mean to multiply e by itself, say, square root of pi times? See, if x is an integer, I understand. If x is a rational number like 3/2, then that means cube e and take the square root. If x is rational, I understand. But what does it mean to multiply e by itself square root of pi times? What it means is go into this infinite series and replace every time you see x square root of pi. And now notice that everything you have is an integral power. Everything is well defined. E to the x is well defined for any input. What this means is the sum, n goes from 0 to infinity of x to the n over n factorial. The sum, n goes from 0 to infinity of y to the m over m factorial. That's what the left-hand side means. Earlier today, I mentioned mathematicians sometimes have bad notation. Whoever did the cosine goes with secant should be short, right? Fortunately, nobody watching this at home can see who nodded in the audience. So if that person's ever found it short, no one will take it as an accomplice to me, an accessory. Right? Sometimes we actually have good notation. It happens. When you see notation like this for e to the x, you think, well, I can just combine the powers. Okay? And so we need to prove that now. So this is the same. I'm not going to worry about justifying all the summation stuff. It's the same as the sum. K goes from 0 to infinity, and then the sum L goes from 0 to K of x to the L, y to the K minus L, divided by L factorial K minus L factorial. What I'm doing is when I have these together, I'm going to say, let's just take all the x and y's such that the sum of their exponents equals a common value. Let's say that common value is k. If the powers of x plus the powers of y equals k, if I have L x's, I have to have k minus L y's. Okay? I'm not proving that I'm allowed to rearrange the series like this. Okay? All right? So you have to justify this. This is where real analysis comes into place. Okay? Does this look familiar to you? What is this looking like? Yes?
The binomial distribution.
Not the binomial distribution, close. The binomial coefficient. Right? What is this missing from being a binomial coefficient? K factorial. So, can we just multiply by K factorial? But if we divide by K factorial, it's fine. And now this over here is just a binomial coefficient. And now your binomial distribution, but the binomial theorem is what's going to come into play. So I can pull the K outside. I have a 1 over K factorial. And now I have the sum, L goes from 0 to K of K choose L, x to the L, y to the K minus L. And now we use the binomial theorem here. And what does the binomial theorem tell us this equals? So what would the binomial theorem tell us for that?
Plus y to k.
X plus y to the k. And so we get the sum, k goes from 0 to infinity, of x plus y to the k over k factorial, which by definition is e to the x plus y. And so that would be a proof modulo this stuff over here where we're somehow changing the summation. Okay? So this is a proof that e to the x, e to the y is e to the x plus y. Okay? Any questions about the exponential function? So what we're doing is we're looking at the Taylor series for the exponential function. And the Taylor coefficients are really nice. They're just 1 over n factorial. And the idea is if your function is nice, the Taylor series coefficients should uniquely determine the function. This is not always the case. Have we done the function e to the negative 1 over x squared in this class? Okay, so consider e to the negative 1 over x squared if x does not equal 0, and 0 if x equals 0. This function is the best example I know of how difficult real analysis can be. If you think about what happens when x is really small, think of x as 1 over a quadrillion. The next squared is 1 over a quadrillion squared. The reciprocal of that is a quadrillion squared. We have e to the negative quadrillion squared. This is essentially 0. If you wanted to plot this function, it would look something like this, where it's extremely flat near the origin. This function is easy to differentiate at every point but 1, whereas the one place where this function is hard to differentiate. At 0. You have to go back and you have to go to the definition of the derivative. So you would have to do e to the negative 1 over h squared minus 0 divided by h. You'd have to use L'Hopital's rule. And so when you do L'Hopital, and you have some strange marks in various places, you get all the derivatives of this function at the origin equals 0. As a really nice exercise, go through, use L'Hopital's rule, and compute that all these derivatives at the origin are 0. If you then try to build the Taylor series, the Taylor series of f is going to be f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial x squared. For this function, its Taylor series is identically 0. The only place where this function is 0 is 0. If you think about it, it's really not that impressive to agree with your Taylor series at 0. Because if you look at what's going on here, all these terms are multiplied by x. So when x equals 0, that's just 0. And then the only thing that survives is the value of your function at 0. So you force the Taylor series to agree with the original function at 0. What's nice about the Taylor series is they will also agree, the first derivative at 0 will be the same, the second derivative will be the same, the third. So you have the same location, the same speed, the same acceleration. But what's going on for this problem is that's the only place where they agree. The radius of convergence, the place where they agree, is 0. This means it is extremely difficult to work with Taylor series. Here is a function whose Taylor series is identically 0, but the function is not identically 0. So hopefully you've seen cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Right? But this would also be the Taylor series of cosine of x plus 341 times our function g of x. With this function over here, we'll call it g of x. If I add 341 times g of x to cosine of x, the Taylor series will be the same. So in terms of trying to determine which function I have, it's extremely difficult. Taylor series have a lot of very bad properties. In complex analysis, it turns out a lot of these things vanish. In complex analysis, if a function is differentiable once, it's infinitely differentiable. Not the case in real analysis. In complex analysis, if you're differentiable once, not only are you infinitely differentiable, but you agree with your Taylor series in the neighborhood. So things are much, much nicer. When we get to the central limit theorem, we're going to need a couple of results from complex analysis. All right. So the last thing I want to do before we stop the clock is, remember, if I is the square root of -1, e to the ix is cosine x plus I sine of x. And the reason for this is just go through the Taylor series expansions. You know what the Taylor series is of cosine, you know what the Taylor series of sine is. If you take e, if I put an I, I'll get 1 ix negative x squared over 2 factorial minus ix cubed over 3 factorial. You'll see all the odd terms will be imaginary, all the even terms will be real, and they'll be alternating positive, negative, positive, negative, positive, negative. So when I put in ix, I'm going to be getting 1 minus x squared plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Those are going to be giving me the cosine of x. And then if I collect all the odd terms, I will get the imaginaries. Okay, any questions? All right, what we're going to do now is we're going to prove all of the trig identities in under 3 minutes. It should be well under 3 minutes. Okay. Anybody want to hit a timer?
Sure.
I'll give you like a ready, set, go.
Okay.
Ready, set, go.
Okay, so e to the ix, e to the minus ix is e to the 0, which is 1. So this is going to be cosine x minus, plus I sine x. This would be cosine x minus I sine x, because the sine of negative x is minus sine of x. When you expand this, you get cosine squared of x plus sine squared of x equals 1, because the cos terms vanish. There's Pythagoras. Take e to the ix, e to the iy, this is e to the ix plus y. If we write this out, we get cosine x plus I sine x, cosine y plus I sine y. We now do cross multiplying. We get cosine x, cosine y minus sine x, sine y, that's the real part, plus I sine x, cosine y, plus cosine x, sine y, and this has to equal the cosine of x plus y plus I sine of x plus y, just by expanding this out. So the cosine of x plus y is this part, cosine x, cosine y minus sine x, sine y. The sine of x plus y is sine x, cosine y plus cosine x, sine y. Anything you want, you just choose appropriately. Done. How long?
That's what you were in 22 seconds.
Okay. Yeah, I knew 3 minutes was way over. Anything you want. If you want to do half-angle identities, try to figure out what you should put in. Maybe try e to the ix halves, e to the ix halves equals e to the ix. Okay? Any trig identity you want, you can get like this. This is much better than, I think, the proofs you might remember. I think if this is angle x and this is angle y, you start drawing things down like this. Right? These are the standard ways of proving things. It also gives you an idea of where these trig identities come from. Why are we having these double angle formulas? These double angle formulas are actually inherited by the exponential function. That's the deep connection behind all this that's going on. Okay, so that's trigonometry. So now you can always derive whatever formulas you want. We've talked about how Taylor series are important. They give us a sense of what's going on. I'll give you a mathematical notebook, which will actually go through and you can just see how quickly the Taylor coefficients merge. Or actually, I'll just give you the video from last year when I just played it and said just watch this time clip, and you can see as you add more and more terms how quickly it converges. For sines and cosines, one of the reasons it converges so quickly is we're dividing by n factorial. So once you get to 10, you're dividing by 10 factorial, which is already sizable. And the nice thing for sines and cosines is they alternate terms. So if you stop after the 10th term and you ask how big is your error, well, there is no 11th term for cosine. The next one that kicks in is the 12th term. So the convergence is extremely fast. Okay, what I want to do now is I want to talk about expected values. So the idea is, if your function is nice, the Taylor series coefficients should determine the function. Okay? Things are not always nice, so we can't always do that, but in principle, if your function is nice, the expected value, the Taylor coefficients give you the function. The same thing is true for probability densities. if you have a nice probability density, if you know its moments, you know the density. Unfortunately, there will be situations where two different probability densities have the same sequence of moments, and you can't determine then which one you actually have. But most of the time, if things are nice, the moments will tell you what's going on. The other thing is, if you think back to Taylor's series, I think on the second day of class we did the birthday problem, and we approximated the logarithm with a straight line approximation. We used calculus to replace a complicated function with a simpler one. We'll use moments like that as well. To try to understand a distribution, the moments give us a lot of information. Okay, so let's talk about moments. So the expected value, we normally write E like this to denote the float of the random variable x is equal to the integral from minus infinity to infinity of x times the density function dx. I'm writing things assuming I have a continuous random variable. If I had a discrete random variable, instead of an integral, I would have a sum. Okay. Not that much of a difference. I want to look at this. Instead of looking at the expected value of x, I could look at the expected value of x to the n. What would that be? How do you think I should change the integral? Yes?
Raise x to the nth power.
Yeah, raise x to the nth power. So x to the n. Or even more generally, if I wanted the expected value of some function of my random variable x, I would just integrate that function times the density. Now, it's not always the case that these moments will exist. Certain moments are so important they get special names. And so, the first moment is called the mean or the expected value. And we typically denote it by mu. Sometimes we'll denote it by mu1. The reason we'll denote it by mu1 is because over here, we'll denote that by mun for the nth moment. Okay? And then one of the things that we often look at is the expected value of x minus the expected value of x to the nth power. And this is called the nth centered moment. And we'll denote that by a prime. I might actually have mixed up which one has the prime and which one doesn't have the prime. One of the biggest things you want to do is you want to compare apples and oranges. Yes? You want to compare things that have different units. You want to add heads and tails. This is something that we want to do, right? We want to compare things with different units. Did I tell you about the Mars probe that made a nice crater? Was that in this class? So there was a Mars probe, and all of the systems were metric except for one system, which was in the English. So when the probe was trying to calculate how much thrust it needed to land safely on Mars, it miscalculated. And you see all these people, as mission control realizes they've just made a $25 million crater in the surface of Mars. You've got to make sure things are matched appropriately. We don't want to compare apples and oranges. We don't want to add heads and tails. This is why we made all of our random variables take on real values. It's similar over here. When I'm looking at probability distributions, I can shift things down, I can adjust the scale, and it's not going to really change things. Is there really a difference between measuring things in Celsius versus Fahrenheit? Is it the same temperature? I get one from the other, I subtract, and then I multiply. So you can think of it as really simple translations and really simple rescalings. Where do you want your 0 point to be? What do you want your fluctuations to be? And so the whole point of the centered moments is I just want to shift my random variable so that the expected value is 0. The next thing when we get to variances, we'll talk about adjusting things so that the variance is 1. We'll control how spread out things are. It's not always possible to do that. So the question is, does every distribution have a finite value for the moments? Or are there some distributions where there's so much probability at large values, things blow up? Can anybody think of a candidate distribution? Yes. Yeah, Cauchy is probably a really good candidate distribution. Yeah. So let's look at the Cauchy distribution. So the mean would be the integral from minus infinity to infinity of x times 1 over pi 1 over 1 plus x squared dx. What does this integral equal? So what would you say this integral equals? What can you tell me about the integrand? What kind of function is it? If I compare its value at say 5 and negative 5, how are those values related? So what's the relation between the value of this at 5 and the value of this at negative 5? Yes. It's the negative. This is an odd function. What's the integral of an odd function over a symmetric region? 0. So you want to say that this has 0 mean. The problem is this is an improper integral. So we have to go back now to Calc 2. How many of you worked carefully with improper integrals in Calc 2? How do you tell if an improper integral converges?
Well, with this you have to break it up into two integrals, and then you keep the limit of the integral.
Which two integrals?
So you need one that'd be from like negative infinity to some constant, and then one from that constant to infinity. And then you take the limit of each of those.
Almost.
Subtract the thing double count.
Nope, no double counting. You are close. What you need to do is you need to look at the limit as a and b go to infinity of the integral from minus a to b of x 1 over pi 1 over 1 plus x squared dx. You are doing a specific cut. I have to look at any way to go to infinity. So there's some really good choices of a and b. What's a good choice of b relative to a? That will make this integral really easy to calculate.
B equals A.
B equals a. So if I take b equals a, it's going to give me 0. Because now I have an odd function over a symmetric region. How about another good choice of b in terms of a? I'm sorry. So my possibility would be 0. I prefer to do 2, but 0 would also work. If I do 2a, well, I'm going to go from minus a to 2a. So minus a to a cancels. And then I have the integral from a to 2a. So I get the integral from a to 2a of x 1 over pi 1 over 1 plus x squared dx. And the question is, what is this integral? Yes?
Isn't it just natural log of 1 over 2 times the natural log?
It's not quite. It's essentially. Right? The difficulty is, if I didn't have the 1 over here, then I would have the function 1 over x, and its antiderivative would be natural log. Okay. You want to say that the antiderivative is natural log. The derivative of natural log is 1 over x. I don't have 1 over x. I have x over 1 plus x squared. X over 1 plus x squared is approximately 1 over x. And it will be, in fact, greater than or equal to 1 over 2x if x is big. And then you could use your argument. But it's not exactly the natural log. The other thing you could do is the derivative of the denominator is 2x. And we have an x up here. So you could probably do a change of variable and calculate it exactly. Okay? I don't really care. I just need to show that this is not equal to 0. We know that this integral is going to be greater than or equal to 1 over 2 pi natural log of x evaluated at a and 2a. And the natural log of 2a minus the natural log of a is just the natural log of 2. So this would be the natural log of 2 over 2 pi, which does not equal 0. Okay. I don't actually care what the value is. All I care is that the value is not 0, and then I got a different answer depending on how I went. Okay? So we could actually calculate out exactly if we wanted to by doing a change of variables, or we could do some kind of trivial bounding. Since I don't care about the actual answer, I would much rather do trivial bounding. So this is an improper integral. Unfortunately, this improper integral does not converge. It depends how you go to infinity. There is no e. Okay? If, however, you are not convinced, and if you really believe that this is just highfalutin advanced mathematics that nobody in the real world cares about, of course, it's symmetric, it should have mean 0, so we calculate the second moment. And so we try to calculate the second moment of the Cauchy. So the Cauchy's second moment. Then we would have the expected value of x squared would be the integral from minus infinity to infinity of x squared 1 over pi 1 over 1 plus x squared dx. I can pull out the pi. I can multiply by 2, and it's 0 to infinity of x squared over 1 plus x squared dx. Well, as x gets very large, what can you say about x squared over 1 plus x squared? What does this look like? So what would this look like for large x? It looks like 1. If the integral is going to converge, then the integrand has to be going to 0 at infinity. Since the integrand is not going to 0 at infinity, it can't converge. This converges to 1, thus integral is infinite. So even if you are able to argue it has a finite mean, by the time you get to the second moment, there's nothing you can do. Okay? Any questions about this? So the question becomes, how can we compute these moments? What do these moments tell us? Which moments are particularly important? So who has taken a stats class? Okay, which are the most important moments in the stats class? Yes?
Isn't like there's a second centered moment?
The second centered moment, the variance. What else?
And in the first one.
And the first moment. If you've ever been in a competitive class and you want to know what was the mean exam, what was the mean score in the final, what was the mean score in the exam, what was the fluctuations, how did I do relative to the mean? One of my friends from high school was a pre-med major at Harvard, and they are so paranoid and competitive there that not only did they give the first 2 moments on the exams, but they actually posted the first 4 moments. So you could really see how you were doing relative to the other pre-med students. Most of the time, the first 2 moments suffice. It is not always easy to calculate moments. So depending on what density you have. So for example, let's consider f of x equals e to the negative x if x is greater than or equal to 0, and 0 if x is less than 0. This turns out to be an exponential random variable. We'll look at exponential random variables in great detail later. You can do it more generally. This is one specific exponential random variable. I could look at maybe f lambda of x is going to be 1 over lambda e to the negative x over lambda, x greater than or equal to 0, lambda greater than 0, and 0 otherwise. And this would be, x would be an exponential random variable with parameter lambda. You have to be careful. Different books have different notations. Some books incorrectly define the exponential not as x divided by lambda, but as x times lambda. And then they have basically, where I have lambda, they have 1 over lambda and vice versa. You can, of course, define it however you want. I think this is a better way. I'm measuring my x's in terms of lambdas. So what I want to do is I want to calculate maybe what is the mean. So the first, of course, is are these random variables? Are these densities of random variables? The non-negative is no problem. Does it integrate to 1? And so here, We were fortunately talking earlier about the exponential function is its own antiderivative. I've got a minus sign, so that's not so bad. So as a quick check, the integral from 0 to infinity of e to the negative x dx would be e to the negative x, and now I flip the order of integration because of the minus sign. And then this would just give us 1. So it is appropriately normalized to be a density. You can check and make sure that the other one I gave you is also a density. And we want to calculate the first moment, or more generally the nth moment. So what would the mean be? The expected value of x would be the integral from 0 to infinity of x e to the minus x dx. Why am I not having the integration go from minus infinity to infinity? Why am I having the integration only go from 0 to infinity? Yes?
Because we have the function, we know the function is 0 for all x less than 0.
The function is 0, right. So if I really wanted to go back to the definition, which I guess I've erased, the definition is I integrate from minus infinity to infinity x, the density of x dx. Well, this density is 0 whenever x is negative. So I can just write the integral from 0 to infinity and save some time. So I have to evaluate this integral. Any thoughts as to how to evaluate this integral? Calc 2, right? How would we evaluate this integral?
Do you look by parts like you usually do?
Yeah, you would do it by parts. So you would say, let u equal, let dv equal. Do you want u to be x, or do you want u to be e to the negative x? You want it to be x. If you make the wrong choice, what do? Try the other. There's not that many possibilities. So we try x, e to the negative x dx. The reason this is a good thing to do is we're trying to decrease. We don't want this power of x. If we do it this way, the power is going to go down. So then we would get du is just 1, v is negative e to the minus x. And then we would get the mean. Let me just write it. Then I'm going to squish things. And so we get the mean is uv at 0 to infinity minus the integral from 0 to infinity of v du. Well, when we look at what's going on at 0 and infinity, when we put in 0, uv is 0. When we put in x equals infinity, we get infinity times e to the negative infinity. So what is the limit as x goes to infinity of x e to the negative x? This is the limit as x goes to infinity of x over e to the x. How do we calculate that limit? L'Hopital, fortunately mentioned earlier today. So when we take the limit of the ratio, because it's infinity over infinity, is the same as the limit of the derivatives. What's the derivative of x? 1. What's the derivative of e to the x? Okay. What some people do by mistake is they would do L'Hopital again. As soon as you don't have 0 over 0 or infinity over infinity, you stop the L'Hopitaling. Okay? And so now, what happens as x goes to infinity? This is just 0. So the whole point of this is this tells us that we don't have to worry about the boundary term uv at 0 and infinity. That just vanishes. So this part goes to 0. And so we are left with the mean is equal to the minus and the minus reinforced, the integral from 0 to infinity of e to the negative x dx, which we've shown earlier is 1. Okay? So this is calculating the first moment of the exponential. If you want to calculate the second moment, you probably have to do integration by parts twice. If I gave you a more general exponential, you would just have a little bit more change of variables. We will see later how to do these in a very fast way. All right, this is a good place to stop. We will continue on Friday.